My name is Julius and I'm a PhD student at the Research Group for Autonomous Robotic Decision Making of Marija Popović at the University of Bonn. Today I will introduce our new work, Informative Path Planning for Active Learning in Areal Semantic Mapping. Semantic segmentation of remote sensing data provides valuable information for monitoring and understanding the environment. Aerial image acquisition is used in many applications, including urban planning and precision agriculture. In parallel, the advent of deep learning for semantic segmentation has opened new frontiers. These developments have expanded the possibilities for the automated interpretation of aerial imagery towards more complex tasks and larger environments. However, deep learning-based semantic segmentation approaches require large amounts of training data that has to be collected and manually labeled in a pixel-wise fashion by human annotators. To alleviate the labeling effort required to train the network, active learning methods have been widely used to optimize the collection of training data. In active learning, the aim is to selectively label data in order to maximize model performance. Applying such methods in the context of autonomous robotic monitoring missions has been largely unaddressed. Recent works examine active learning with imagery acquired by low-cost UAVs. However, these studies only consider selecting images from a static pool obtained from previous exhaustive aerial surveys. Usually, these large unlabeled datasets do not exist or cannot be easily transferred to different terrains, as visual appearance differ vastly from application to application. To tackle these challenges in aerial semantic mapping, we propose a planning framework for active learning in UAV-based terrain monitoring. We estimate model uncertainty in semantic segmentation and fuse it in global terrain maps. Based on the map, our planning approach guides the UAV to collect most useful training images for labeling. In this way, our pipeline aims to reduce the number of images that must be labeled by a human annotator. Our proposed planning framework is overviewed as follows. We start with a pre-trained network for semantic segmentation deployed on a UAV. During a mission, the network processes images to predict semantics and model uncertainties, which are fused into a global map. Based on the UAV position and the current map state, our algorithm plans paths for the UAV to collect the most uncertain training data for improving their network performance. After the mission, the collected images are labeled by an annotator and used for network retraining. To achieve this goal, we propose a lightweight neural network based on the ERFnet architecture able to estimate the model uncertainty. Input to our network is an RGB image and outputs are semantic labels and model uncertainties. Our Bayesian ERFnet uses Monte Carlo dropout to approximate the posterior distribution over its model parameters in a computationally traceable way. On the right, one can see from left to right the input image, ground truth, predicted semantic labels, and the model uncertainties. The qualitative results with Bayesian ERFnet trained on the ISPRS Potsdam dataset show high model uncertainty in misclassified regions. On the left, we display our Bayesian ERFnet with varying Monte Carlo dropout samples at inference time in blue compared against a non-Bayesian ERFnet in orange on the ISPRS Potsdam dataset. For 50 Monte Carlo samples, the Bayesian ERFnet improves mean IOU by 3.1% and reduces the expected calibration error by 7.6%. Further, we develop informative path planning algorithms to guide a UAV to adaptively collect useful training data for our network. Our goal is to plan paths to gather new images that maximize the model uncertainty. The terrain is initially unknown and the UAV is constrained by a maximal flight time. A key feature of our approach is to relate the information criterion to the active learning acquisition function. This means we plan paths to collect new images, maximizing the model's performance gain when added to the training set. Therefore, we approximate model performance gains with model uncertainty. To this end, we plan paths maximizing model uncertainties stored in the global map. Further, we normalize the model uncertainties by counting how often a pixel measurement already occurs in the training dataset to foster trained data diversity. Last, we assign an exploration bonus to not yet visited terrain areas. We propose 3 planners to solve the above path optimization problem. First, our image-based planner follows the direction of the highest estimated model uncertainty in the image recorded at the current UAV position. Second, our frontier-based planner navigates to the most uncertain boundaries of explored terrain given the current state of the global uncertainty map. Third, our fixed horizon planner reasons about images taken over multiple time steps. A non-myopic evolutionary optimization routine is applied to refine the greedy solution in the continuous UAV workspace. Evaluate the behavior and performance of our proposed planning framework. Qualitatively, the planned paths confirm the adaptive behavior of our approaches targeting regions of high model uncertainty. Quantitatively, better active learning performance is reflected by maximizing accuracy and mean IOU with less acquired labeled images. As indicated by steeper rising curves, our proposed fixed horizon and image-based strategies, in orange and purple respectively, clearly outperform a classical coverage-based baseline in yellow, since they allow active decision-making for data collection. To summarize, we introduced a general path planning framework for active learning in aerial semantic mapping scenarios. Our framework exploits a Bayesian network to estimate model uncertainty in semantic segmentation. A key aspect of our work is that we link the map model uncertainty to a planning objective, guiding UAVs to collect the most informative images for network training. This pipeline reduces the total number of images that must be labeled to maximize segmentation performance, thus conserving human effort, time, and cost. We open sourced our code for usage, benchmarking, and development by the community.